All right, we ready to continue? Mr. Blackman asked a question during our break. He said, what about problem number 39? So problem number 39 is actually kind of similar, except that the pressure changes and the volume changes. And so how do you deal with boundary work in that kind of a problem? Well, what did it say that the system started out at? Let me back up.
Specs?
Yeah, well, let me back up just a little. How do we calculate boundary work? We integrate pressure over volume. And essentially, the equations I've given you so far said if I know how pressure depends on volume, then I can integrate it this way. If it depends a different way, I integrate it a different way. Okay? So, but really, what are you doing? What you're doing is you're saying, give me what the curve shape is, and I'll tell you what the area under that curve is, and that area is boundary work. That's what we're doing. Does that make sense? Makes sense? Is it better now? Okay, so let's see what we've got. We're moving from one state to another. So give me what you know about those two states. Here's state one, and I'm going to put state two over here because I know that as the volume increases, the pressure is also going to increase. So what do you know about either state?
At state one, it is 200 kilopascals.
So that tells us here, right? 200 kilopascals. And what else?
At 0.4 cubic meters.
0.4 cubic meters. Good. Do we know anything about state two?
250 kilopascals.
Okay. Anything about volume?
0.6 cubic meters.
So basically all we're going to do is figure out what this area is. And the way I would do that is by taking the average pressure right here and multiply it by that distance. So boundary work would be equal to 0.6 less 0.4, and that is cubic meters, multiplied by an average pressure of 225 kilopascals. There's the boundary. Make sense?
I'll have to get back to you on that because I think I might have tried something like that,
Okay.
but East didn't agree.
Okay. Well, they said it's a linear spring. And so the pressure and the volume would have to depend on each other linearly. Because there's no way for the, I mean, if the pressure goes up too high, the spring is going to compress, right? So it has to follow that curve. Anything else on that problem or any other?
I can backtrack, but we never did the PV diagram for 38.
Oh, thank you. You're right, we did.
It actually,
Would be the same.
No, the PV diagram for that would look a little bit different.
it's a horizontal line, right?
Yeah.
Right, essentially, it's a horizontal line, right? Because we went from, now that's probably, I think they wanted to know it with respect to saturation lines.
Yeah.
And so let me draw a generic vapor dome. We know we started out with all liquid, so we were on the liquid line, the saturated liquid. You know, we ended up at 50% quality, so about there maybe. And so whatever the pressure, I think was 175 kilopascals in that problem. And we started off at a specific volume of VF at P of 175, right? Whatever it was. We looked it up. I know it was 0.001 something, right? It had to be.
So you wouldn't use the volume that they gave you, the .005,
Are you talking about this problem or that problem?
that one.
What about this one?
They gave you a volume state
I see.
one.
Would I put, no, I would prefer to put specific volumes there.
Specific volume.
Okay.
So when you do a PV diagram, it should always be with specific volumes.
Well, unless you want total work, like you want here. Our purpose was different here. We're trying to get boundary work. Now, if you wanted work from a PV diagram where you're using specific volume, you could still get this volume here once you figure out what your average specific volume is here, and multiply by the total amount of mass. Right? Because we really did that, right? This is V1. This was V2, where it was equal to specific volume of saturated liquid plus quality in state 2, DFG. Right? Whatever that number was, I think it was 0.5 or something.
Yeah, it's right on.
So basically, when you have like pressure and volume, if you're dealing with something in the realm of an ideal gas, you can just pretty much interchange pressure and volume with PV with PV. Little p.
It doesn't matter if it's an ideal gas or not. In fact, in this problem, we weren't dealing with an ideal gas because we had a bunch of liquid in it. So it doesn't matter if it's ideal or not, ideal gas. Yeah, anytime you're dealing with volume, you may deal with specific volume or total volume.
You just gotta make sure you leave mass in it.
Right.
If you-
Well, really all you're doing is you're looking at the volume per unit mass.
So but if you don't need to have it per mass, then you might as well, like that, 'cause you're taking away one unit still.
Sure, sorry. Good questions, what else?
Number 16.
Yes.
It asks for the final volume. It gives you a bunch of stuff. I use P1V1 equals P2V2.
Okay. Why would you do that?
Because I had three of those four components for no.
Well, let me ask you a question. When would P1, when would when would PV be a constant? Because what they told you here is P times V to the N is a constant. That's different than saying PV is a constant. If you had an ideal gas at constant temperature, then PV would be a constant, because for an ideal gas, PV equals nRT. So if P and V are constants, that must mean that the temperature is constant. Make sense? Now, in this case, what they've actually told us is that PV raised to some power n is equal to constant. Students at your level typically are really uncomfortable with this because you feel like, what's this N and C stuff? What is all this stuff? Where did it come from? This is just kind of like another ideal gas equation. You remember when you accepted this? Remember in chemistry class when the professor showed, or the teacher, or whoever you learned from showed it to you? You're like, where the heck does this come from? They gave some little explanation that didn't make any sense. You just accepted it and started using it. Eventually you use it for gases like air especially, right? Well, that's the same thing you really need to do here. Why does it behave this way? It doesn't matter. Some do. And when they do, you can use this. Now, how would you know that it's behaving that way? Well, it turns out if you have a balloon that has very little elasticity, it doesn't take much to stretch it. If the pressure is proportional, I think, to the diameter, I can't remember, then you will have, and it's an ideal gas, it'll behave polytropic. Okay? That's one situation where it can happen. Okay? But it's so common that you can counter situations where a gas is obeying a polytropic form of equation, that we go ahead and use it, because we need to know something about it. Just like it's so common when the ideal gas law is used, right? Because so many gases behave ideally, you just use it. So anyway, calculate the work done when a gas expands from 350 kilopascals. Now be careful, this is important, 350 kilopascals. And a volume, 0.03, thank you, cubic meters, to a final volume of 0.02. So V2, 0.2 cubic meters, N is 1.5. Now, they've given us this, but how the heck are you going to get C? Well, they've already given you a point. You just calculate 350 kilopascals multiplied by V, 0.03 cubic meters raised to the 1.5 power equals the constant you're looking for. It's just a number.
1.819.
Okay.
And then to find out pressure at stage 2, don't you just use P2 equals C times V to the negative N?
You got it. So there's two ways of going about it. The way I was going to go is what you're saying. You can rearrange the equation, say that P2 must be equal to C over V2 to the N. Now you got C and you got N. If you don't want to mess with C, you don't want to calculate, you don't have to. Because all they asked for was boundary work, right? They said, tell us the boundary work, and if you look up the boundary work for a polytropic process, you'll find it says P2, V2 less P1, V1 over 1 minus N. Is that what you found? What you're using? Okay. So your question becomes, I know P1, V1, how can I figure out P2, V2? If you set them equal to each other, that doesn't make any sense because then there's no boundary work. Okay? And they're not equal anyway. So if this is a constant, couldn't you say P1, V1 to the N equals P2, V2 to the N? Right? And then you could solve for it because all you really want, I guess the easiest thing to do.
Was listen to Isaac, that's what he told me when we were sitting down there.
Okay. All right. So V2 would be equal to, let's see. Well, let me not go that quick. I'll mess up myself. V2 over V1 to the N, collecting the two volumes together, are equal to P1 over P2. And so V2 over V1 would be equal to P1 over P2 to the 1 over N. Don't be afraid of exponent laws. You may have to look them up. Basically what I did is I raised both sides to the 1 over N power. N over N is 1, and so I end up with just a 1 here. So then finally, we're not going to use C, and we don't really need it. We would just say V2. What did I solve for V2? I wanted P2. I don't know where my head is. Let me try again. P2, just moving it over here, is P1, V1 over V2 to the N.
But when I say, where you have the P1, V1N equals P2, V2, and that's what, because we were sitting down at the table working the homework,
Yeah, sure.
and he threw that out there. I was like, no way, crazy thought. Walk away.
Well, it's just polytropic. All it says is that, I mean, the polytropic behavior says that if you take pressure times volume at the end, you get a constant. So it wouldn't matter if you take it at state 1 or state 2, it'd be the same constant.
I understood this problem a lot better before you started talking about it.
Well, that means I need to be fired. That's the exact opposite of my job.
No, it's okay.
What else? Well, we need to talk about an exam, and I usually like to have an exam really after chapter 4, but it can include chapter 5 if you wanted to, it doesn't matter. Oh, by the way, Mr. Blackman, look at page 169, I think you'll see something interesting there. Look at the schematic on 169.
Aren't you just gonna keep giving us the little tests, or did you change your mind about something?
You're right, I forgot. We're doing little tests, aren't we? Never mind.
I was wondering where we were leading.
Look, all those don't count.
Those are practice. No, you're right, we're doing mini tests, aren't we? So there's not a big exam coming, good.
So next time we'll take the third.
Yeah, next time we'll take the third. Now, so far we've covered chapter 1 and 2, I think, in the quizzams, right?
Yeah.
So the next one's gonna be over, chapter
Next there should be chapter 3, which properties of pure substances, but when we get to the end of it, we're really talking about, let's see, yeah, that's right, properties of pure substances. Okay, so probably, I'll go ahead and give you guys a hint. It'll probably be over compressibility. I like compressibility. Yep. Most likely, so make sure you understand that. And then the next one after that would be chapter 4, and that'll be boundary work, of course. What else? Okay. Well, if you don't have more questions, then let's move forward into chapter 5. What I'm really trying to do is get through chapter 5, 6, and 7. Because by the time I get through those, you guys will be well prepared for your project. Okay? But 6 and 7 have to do with entropy. Entropy is a property that's really useful to know about so that you can apply it and use it. So I just want to get to that point. so that you guys have all the tools you need for solving or creating something that works in the project. All right, so chapter 4. We've talked about closed systems and not a whole lot about open systems, somewhat. Now, we know that there's conservation of energy and conservation of mass, and just for the fun of putting it up on the board, we get to write down Einstein's equation as if we're actually going to use it, right? Okay, where you can actually change mass into energy, and I think people have successfully changed energy into mass, but I'm not sure about that. Theoretically, it could be done. Okay? But anyway, the point is that since this is the speed of light squared, if you multiply that by a small amount of mass, you get a tremendous amount of energy out. But for the purposes of this class, we're not going to be talking about any nuclear reactions. So we won't be dealing with any transformation of mass to energy. And as far as we're concerned, energy is conserved and mass is conserved, okay, independently. Even though you get to go back and forth between the two. So to deal with it, we have to somehow deal with mass flow rates. We've already talked about mass a little bit. We really haven't used a mass balance per se. So we'll start talking about mass flow rates and volume flow rates and other things. You guys have seen this before. The idea is that if I want to somehow measure how much mass is passing per time, why would I care about that? Well, if I've got a turbocharged engine, I'm very interested in the mass flow rate of air going through the engine, right? So I want to measure that. I want to know what's going on. Because the higher the mass flow rate through the engine, the more power the engine is going to put out, assuming I add some more fuel. So this is pretty interesting stuff. So anyway, in order to figure out the mass flow rate or relate it to other things that we already know, we can integrate across the cross-sectional area flow and add up all the small velocities of flow times density. That would give us times that small area, would give us a small mass flow rate through that little square there that I've got. If we integrate, in other words, if we add up over the whole area, we add all those small mass flow rates that occur everywhere on the surface through that surface, then we would end up with a total mass flow rate. And if you've had 313 or you're about to take it, you will find out that in laminar flow, there's a velocity profile that is parabolic in shape. And actually, the velocity of flow is highest along the center line, 0 at the walls. It actually sticks to the walls. Okay, now, for this class, we don't care about that. What we're going to do is use an average velocity. Instead of some maximum velocity or some minimum velocity, we're going to use an average velocity. So if you ever go out to the field and you're working as an engineer and you go to measure flow rates, you find that there's a flow rate in the center that's twice what you expect it to be. You probably have laminar flow, and you're thinking of average velocity instead of the fact that there's actually a profile. But 9 times out of 10, using the average velocity is what we need to do. So in this class, instead of performing this actual integration so that we can avoid it, what we're going to do is use the average velocity so that both density and velocity, assuming incompressible flow, can come out of the integral. And all we're doing then is multiplying density times average velocity times cross-sectional area. Okay, so this is a really handy equation. If you understood all that, great. What you need is in the box over here. We can talk about volumetric flow in the same way, except instead of needing density, we simply don't need it anymore. We multiply the velocity of flow times the cross-sectional area flow, add up all the small cross-sectional volumetric flows, and end up with a total volume flow. Now, normally, again, we will take the velocity to be some average value so that it will come out of the integral, and we end up with just the velocity of flow.
Could you go back to slide, actually?
Yes. There's one equation missing here I want to add. Were you doing that?
Yeah, that's what.
Okay, you got a question or you just want to write something down?
Just writing down.
In fact, I just realized this equation should be on the next slide as well. It should be, well, I guess it didn't let me copy, hang on.
So the little weird B, that's just velocity.
That's just velocity, that's correct.
We have like 8 different V's.
I know. One of the worst parts of this class is all the V's. Usually capital V with a dot on it means volumetric flow rate.
Velocity and specific volumes are the two that I'm confused.
Yeah.
They're both a little.
There we go. So that's what should be on the slide. I mean, I've avoided having it all this time. But the point is that most of the time, we're gonna take V to, the little v to be an average velocity, we pull it out of the integral, and then the integral just gives us the total cross-sectional area with it up. Okay. Notice that the equation here looks a lot like the equation on the previous slide. Looks a lot like this. The only difference is this one has density in it and gives us mass flow rate, and this one doesn't have density in it and gives us volume flow rate. Well, it turns out you can relate mass flow rate to volume flow rate. Mass flow rate is density times volume flow rate. Since density is the inverse of specific volume, you can write that as mass flow rate is volume flow rate divided by specific volume. Okay. So once again, these are just handy equations that you.
So that little v was specific volume, not velocity.
I know, it's bad, isn't it? Here's what I do, not in the slides, but in handwriting. What I do is I make a script V for velocity. I make a capital V for volume. I make a lowercase v for specific volume. Okay, in my handwriting, that's kind of the legend. I'll put a little arm on it to show that it's a small v. In the slides, I use this, which is also a script v. It's just not as obvious. And the only reason I do that is because that's what your book does. I want to be consistent with it.
So that V average is
Average velocity.
average velocity.
Got it.
Okay.
That's right. Good conversation. Anything else? Okay. Now, we hadn't gone into chapter 5 slides yet last time, correct? Okay, I didn't think we had. All right, so we've dealt with an energy balance, but now we're going to deal with mass balance. Now, a mass balance is the exact same analogy that I use for an energy balance. We're going to think about it as a bank account account. Since it's something that's conserved, then it's something that's not created or destroyed, then we can balance it, right? Just like ideally dollars are not created or destroyed, right? I know sometimes it seems like it. You look at your bank account, it looks like dollars have been destroyed, but unless there's been thievery, which is essentially a transfer, so they're not destroyed anyway, dollars are not destroyed. Now, what really does destroy your dollars is interest, but we won't talk about that. Anyway, so the total mass entering a control volume, we consider some control volume, and over some time t, delta t, we allow mass to enter it. The total mass that enters the control volume, less the total mass that leaves the control volume during that time, is equal to the net change of mass inside of the control volume. In other words, I've got a bucket that's empty, and I take a hose and I squirt water into it at a flow rate of 10 GPM for 1 minute. Then my initial balance in the bucket was 0. My final balance in the bucket is 10, because I transferred 10 in there. Right? If I then take it over and I water 2 trees, where I pour 5 gallons on one tree and 5 on the other, I'm back to a balance of 0. There's been a change of mass in the control volume. Okay, does that make sense? It's very straightforward. It's the same thing as the energy balance. In fact, the mass balance, in my opinion, is easier to deal with than the energy balance. Now, if we're interested in flow rates instead of just total flow, then we can divide both sides of the equation by the amount of time that we allow the flow to occur. So however much mass flows during that time, and we could talk about the mass flow rate. We'll use a dot to indicate that. So the mass flow rate coming in less the mass flow rate coming out is the rate of change of mass in the control volume. This side over here looks a little scary, so let's clarify it. Remember the bucket a minute ago? Say that bucket had a leak in it. So I've got my garden hose and I'm pouring water into that bucket at a rate of 5 gallons per minute. Okay, that's pretty high flow rate, but let's just say that's what I'm doing. Mass flow rate in is 5 gallons per minute. Let's say that the flow rate out, the hole is just the right size so that the flow rate out is 1 gallon per minute. Then how quickly am I changing the mass in the control volume? By 4 gallons per minute, right? Now, to appeal to your intuition, I use volume instead of mass, okay? Because we don't usually think of volume, especially when we think about a garden hose and a bucket, right? But it's the same thing for mass, right? If mass is flowing in at a rate of 5 kilograms per minute, flowing out at a rate of 1 kilogram per minute, then the control volume is increasing mass by 4 kilograms per minute. Make sense? Okay, so essentially, the first term is the rate at which mass enters, second is the rate at which it leaves, and the last term on the right-hand side is the rate of change of mass in the control volume. Now, there are mass balances that you probably don't want to deal with. Here's one of them. I put it in here mainly to make you appreciate what we've done for you in the book, the kind of problems I gave you. This is where you've got a generic control volume, and what's happening is you consider some differential area. There's a normal to that area, that's a vector that's perpendicular to the area, and there's a velocity of fluid flow through that area that is not at the same angle as the normal, maybe off angle. So you actually have to take the dot product of those two in order to deal with all of the flow that's going through what's called a control surface. That's what CN stands for. And you relate that to the rate of change of mass in the control volume, where CV is the control volume. So basically you have to add up over all of the volume. That's what the integral does, and add up over the whole control surface to solve any problem using this kind of mass balance. Fortunately, you won't have to deal with that because we're going to make it a little bit simpler. If there are areas that are defined as inlets and outlets, so there's only certain areas of flow, then we might have to integrate over all those areas in and out. In other words, if you have a pipe with a cross section, say a 2-inch pipe or so, you might have to add up over that entire cross-sectional area for each inlet and each outlet. And that's what the integral is here. We do. It's just expanding this term into two different parts. Okay? Now we're going to get to something that you can use in just a minute. To make this look a little simpler, instead of worrying about this integral here, if once again we take some average velocity, pull it out of the integral, assume the density is constant, pull it out. Notice this rho v dA basically becomes m dot n, it's integrated just like it did on a few slides ago. Okay? So this is just a mass flow rate. So is this. It's just that this one's out and this one's in. And this term just becomes the rate of change of mass in the control volume. Okay? We're going to push the easy button and say, well, what happens to this thing when the flow rate in is equal to the flow rate out? So if you've got a hole in your bucket, you're essentially pouring water through the bucket, right? The flow rate in equals the flow rate out. There's no accumulation of mass within the volume, okay? And so there's no rate of change of mass in the control volume, so that goes away. Basically, the mass flow rate in equals the mass flow rate out. Furthermore, if the density is always the same at all inlets and exits, then the volume flow rate in is equal to the volume flow rate out. And that's what I described to you a few minutes ago when I was talking about gallons per minute of water flowing into and out of the bucket. For a single stream, steady flow, this is even easier. The mass flow rate in equals the mass flow rate out. Now, you may look at this and say, well, that seems quite obvious. But what if I gave you a problem like this? We'll get to problems later when we talk about expansion valves, and we may as well go ahead and talk about them now because you need to be quite familiar with all the different components used in refrigeration. In refrigeration, what you commonly do is make a gas go up to high pressure. It gets hot, so you cool it down at high pressure, then you let it expand. And when it expands, it cools down. And you use that cold gas to refrigerate something. Okay? Now in a heat pump, you use that cold gas to refrigerate the outdoors. Pump heat into the home. But in this case, how many inlets and outlets do I have if I got flow going from here to here? One inlet, one exit, right? If this is a steady flow, and you got 5 kilograms coming per minute in here, there will be 5 kilograms leaving here. Now here's where it gets a little scary. You might begin to be intimidated if you know that what comes into this is a saturated liquid, but what leaves is a saturated liquid vapor mixture. So the phases are different, right? There's one phase coming in of all liquid, there's 2 phases leaving, because you allow the pressure to come off of it. So a little bit of it boiled off, not all of it, but some of it. Okay? But yet, even still, the mass flow rate in equals the mass flow rate out. It doesn't matter that some of it's in the vapor phase or the liquid phase, it's the same thing. Okay? We're just talking about the mass flow rate, and this operates at steady state, so this still applies. So we could, now in the case where we have a single phase, we can talk about the density times the velocity flow times the cross-sectional area flow coming in, and density, velocity, cross-sectional area flow leaving. This won't work very well for this side, because we have two different densities. We have a density of liquid and a density of vapor. This can only accommodate one of the densities. So how can we modify the equation to make it work?
Quality.
Quality, well, how about like this?
Multiply any on one of these.
My script V. How about if we break this up into two parts? There's this part here and this part here, right? The flow coming out in the gas phase versus the liquid phase can be quantified like this. There's mass flow coming out in the gas phase, mass flow coming out in the liquid phase. So this would just be the density of the saturated vapor, which is G, multiplied by the velocity. Now this is not specific volume, so I'm not going to put a subscript G in here because I don't want confusion. Okay. Multiplied by the cross-sectional area flow, just the gas itself. I don't know how useful this would be, but it could be done. Now there may be a different velocity of flow for the two, but let's just assume the velocity of flow for both the liquid and the vapor are the same, because otherwise if they weren't, then the relative amounts of liquid and vapor would change. Okay? So basically what I'm saying is that, let me do it this way, mass flow rate N equals the mass flow rate of the saturated liquid plus the mass flow rate of the saturated vapor. I said that backwards, vapor. So we could write this as rho 1 V1 A1 equals rho G V AG plus rho F V. Okay, so you could actually extend this a little bit if you wanted to. I don't know how useful it would be, but you can do it. But most of the time with a problem like that, we're just interested in the total mass flow rate. Now, in the case where we have a single stream that is uncompressible, so that the density is the same at the inlet and exit, we could use a volume balance, if you will, a volume flow rate balance, where the volumetric flow rate coming in and leaving are the same. Could we say that the volumetric flow rate coming in and leaving are the same here? Absolutely not, because the gas has a much lower density. So that equation wouldn't help us at all in that particular problem. Now, unfortunately, we've sort of already covered this. We've encountered it, I should say. But we haven't gotten to talk about it until here we are in chapter 5. Because technically we really haven't done a lot with open systems until we get to chapter 5. So if you have a non-flowing fluid, that non-flowing fluid can carry three types of energy. It can carry thermal energy, kinetic energy, and potential energy. Remember when we talked about flow energy? Had the control volume, I said imagine a piston pushing element of fluid into the control volume. Okay. Well, in that case, there would also be flow energy in addition to the thermal energy. In other words, in addition to the temperature, if you will, that the fluid carries into the control volume with it. So we have to account for that flow energy as well, because it can be large. It can be significant. And if you notice, this is really the reason that we define enthalpy. The summation of the thermal energy and the flow energy are thermal energy. There was one time when the president of a company I worked for, I won't tell you which one, but they were talking about enthalpy, and you could tell they didn't actually understand it. Because they were saying, well, what is enthalpy? We need to describe enthalpy. We've got to figure out, we've got to explain exactly what enthalpy really is. We were all saying, well, it's just something that's made up. And they didn't like that answer. But that's what it is. It's just something that's made up, because enthalpy doesn't exist. It's just a combination of two other things. Just internal energy plus flow energy. Nothing more, nothing less. They appear together so often, it's easy to just talk about them with one word, or one number. So this theta quantifies how much energy a flowing stream will carry with it per unit mass, whereas E will be used for the amount of energy per unit mass for a non-flowing stream. So finally, we get to really talk about energy transport by mass, and really we've already looked at this, right? Because we talked about it a little bit with the question we had on the quiz exam, right? where we were only dealing with a couple of terms. We were dealing with the flow energy and the potential energy, but not thermal or kinetic energy. Okay? So more generally, mass can carry with it 4 different forms of energy. Now, I have let the slide go by that says what the forms of energy are. Let's see if you understand what they are. You might remember. What forms of energy might mass carry with it coming into a control volume?
Flow and
Potential energy, so a GZ term. Flow energy, a PV term. What else? Kinetic energy, a V squared over 2 term. And thermal. Good. So you guys know this stuff. This is not so hard.
Sounds like a good test question.
Yeah, worth about 50 points.
Yeah, and then the next student says, we've already had the test question. We just passed. Give us our 50 points. Arguing from a state of having nothing to a state of having something. Okay, so anyway, so if we multiply the mass flow rate times the amount of energy that each unit mass carries with it, then we have a way of quantifying energy being carried into a system via mass. So anyway, so here it is all multiplied out. See, that equation is important. We'll use it quite a bit. Okay, now a lot of times what will happen is the kinetic and potential energy terms will be very small by comparison to the sum of the flow and thermal energies. So a lot of times these will cross off, and the way we will quantify the amount of energy carried into a control volume by mass is just the enthalpy times the mass flow rate. Now, we're going to develop the steady state energy balance as well. Am I out of time, or are we doing okay? We've got a few minutes, so let me get through this slide and we'll be done. This is a good place to stop. So if we look at a steady flow system, a system that is not changing with respect to time, then we could talk about the energy flow rate coming into the system being equal to the energy flow rate leaving. Let me take your car as an example. What kind of mass flows into your car? Well, not gas, because the gas is already in the tank, right? And let's neglect the flow rate of the gas, because essentially it's combustion products coming out of the tailpipe. But actually, if you look at the amount of mass of gasoline versus air that flows through your car, there's a whole lot more air that flows through your car than gasoline in terms of mass, which may surprise you, but that's true. Anyway, so essentially, you have air flowing into the intake and air flowing out of the exhaust pipe. Now, if it's a car like my truck, you've also got a couple of leaks before the muffler, so there's some exhaust coming out there too. But the point is that the net rate of energy transfer in equals the net rate of energy transfer out. So just talking about the mass, because with the car there are other energy flows too, right? Your engine's hot, and so it's losing energy to the surroundings. There's also work being extracted from your car, pushing the car down the road, right? But just talking about the flow rate through the engine, the airflow rate through the engine, okay? The rate of that flow through the engine is essentially constant. Your car operates at steady state, okay? Assuming you're on the highway and moving at a reasonable speed. So anyway, in a steady state energy balance, what we're doing is we're talking about a system where the flow is steady, it's fully developed, it's not changing with respect to time, and all we're talking about is energy. Now, of course, there are more ways of carrying energy around into and out of the system besides just mass, right? Mass can carry energy in and carry energy out. And if you have multiple inlets and multiple exits, like the many holes on my muffler, okay, then all those will carry energy out. That mass, that air will carry energy with it. But there can also be heat transfer in and work transfer into the system, as well as heat and work transfer out of the system. So there can be flow rates of heat in and work in and heat out and work out. Now if we expand that theta so that we can look at all the different ways that the mass carries energy with it, the kinetic potential and enthalpy, which is flow energy and thermal energy, then we have an equation that's actually very important. This is an equation on page 233. You want to bookmark it when you get home if you've already cut up your book, okay, because that's a pretty handy equation. Or just know that it's in the back of chapter 5. Okay? I think it is. Let me double check that. Chapter 5. Yeah, you may want to write it into the back of chapter 5. your author kind of went back to a energy balance that has a sign convention in it, but I like this one a lot better with Q in and Q out, W in and W out. So we want to jot that down. Now, what if we were to divide both sides of this equation by the mass flow rate? What would happen? Well, if we look at the Q and the W terms, what would happen is the heat transfer rate per the mass transfer rate would just be the specific heat transfer. So it'd be the amount of heat being carried into the system per mass that's in the system already. Does that make sense? Wn, little Wn would be the work flow rate in, the power flow rate in, essentially divided by the mass flow rate in. Okay? And so that would be a specific work as well. And I misspoke. I said this would be per unit mass of what's in the control order. That's not right. It would be per unit mass that's flowing in. Okay? So every unit of mass that flows through has a certain amount of heat that comes into the system to meet with that mass. Moving all of the heat and work terms to one side, we'd end up with this. Moving all the mass flow terms, the mass flow, or the energy carried by mass to the other side, we'd end up with these. Notice the mass flow rates just cancel out. But here's what I want to point out. I'd like for you to write this down in your book, like I said, when you get home.
Which one?
Probably both of them. They're both have boxes around them. I don't think that your author has either one in the back of chapter 5, but they're both handy. Here's what I want you to do though, on this equation, it's critical that you understand this is for steady flow. There is a mass flow rate associated with this equation. It just doesn't appear in the equation. This equation can't talk about something that's not flowing because it has enthalpy. And it has mass flowing in and out, okay? And so just don't forget that when you use this equation, even though it looks like there's no mass flow rate, there will be mass flow rate in the problem. Okay?
So it's steady flow.
It's steady flow, that's right. All right, next time we will talk about all the wonderful
Now
devices.
you're gonna have to go back there, I'm trying to write that down.
Oh, sorry. There you go.
Just write this down, but I'm not gonna let you see it.
Well, it's in the slides. I assume you guys download the slides. Keep it.
I was just messing with you.